Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night, but probably won't. Imagine you're standing on a perfectly still road, watching a car drive past at 60 miles per hour. If you were to jump into another car and drive in the same direction at 30 miles per hour, that first car would now appear to be moving away from you at 30 miles per hour. Simple, right? Relative speeds are intuitive. But what if that car was a beam of light? And what if no matter how fast you drove towards it, or away from it, or even if you just stood still, that beam of light always appeared to be moving at exactly the same speed, 622 miles per second, or roughly 300,000 kilometers per second? This isn't a thought experiment where the rules of physics are bent for fun. This is how our universe actually works. The speed of light in a vacuum, often denoted as q, is not just incredibly fast. It's an absolute, unyielding cosmic speed limit. It doesn't matter if you're chasing it at a spaceship going 99.9% the speed of light, or if you're standing still on Earth. Light always zips past you at cork. This single mind-bending fact, confirmed by countless experiments and enshrined in Einstein's theories of relativity, completely shatters our everyday intuition about speed, time and space. It's the foundational principle that makes faster-than-light travel not just difficult, but fundamentally impossible, and it's the key to understanding why attempting to break this speed limit inevitably leads to the most mind-bending concept imaginable: time paradoxes. We're talking about situations where cause and effect could be reversed, where your future could influence your past, or where you could arrive at your destination before you even left. It sounds like science fiction, but it's a direct, unavoidable consequence of the universe's most fundamental speed limit. And the journey to understanding this will reveal the true interconnected nature of space and time. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Chapter 1. The Unyielding Speed Limit. Why Light Just Won't Be Rushed. We'll understand why the speed of light isn't just a fast number, but a fundamental barrier that shapes the very fabric of reality. Let's start with a fact that seems to defy all logic, yet is one of the most rigorously tested and proven aspects of our universe. No matter how fast you are moving, a beam of light will always appear to be moving away from you at exactly the same speed. Not almost the same speed, but precisely the same speed. This isn't like trying to catch up to a car, it's like trying to catch up to a car that moves faster the faster you drive, but somehow still maintains the same relative speed. It's utterly counterintuitive, and it's the bedrock upon which the entire universe is built. So what exactly is this speed of light? In a vacuum, it's approximately 258 meters per second. To give you a sense of scale, that's fast enough to circle the Earth's equator about 7.5 times in a single second. From the Sun to the Earth, about 8 minutes and 20 seconds. These are vast distances covered in fractions of time that our brains struggle to comprehend. But the sheer speed isn't the truly mind-bending part. The truly revolutionary insight, the one that broke classical physics, is that this speed is constant for all inertial observers. An inertial observer is just someone who isn't accelerating, someone moving at a constant velocity. Imagine two spaceships. Spaceship A is stationary and a light beam passes it at key. Spaceship B is zipping along at half the speed of light, chasing that same light beam. According to our everyday intuition, the light beam should appear to move away from Spaceship B at only half its usual speed. But that's not what happens. From the perspective of Spaceship B, the light beam still zips away at k. It's like trying to run on a treadmill, but the treadmill automatically adjusts its speed so that you're always running at the same maximum pace relative to the ground, no matter how fast you try to go. This constancy of the speed of light, first hinted at by the James Clerk Maxwell's equations for electromagnetism, was a profound puzzle, challenging centuries of Newtonian physics. This exact puzzle led to one of the most famous experiments in scientific history, the Michelson-Morley experiment in 1887. Before this, scientists believed that light, like sound waves, must travel through some kind of medium, a luminiferous ether permeating all of space. If such an ether existed, then the Earth, as it orbited the Sun, would be moving through this ether, creating an ether wind. Light travelling with this wind should have a slightly different speed than light travelling against it. Michelson and Morley designed an incredibly precise interferometer to detect this ether wind. They split a beam of light, sent the beams along perpendicular paths, reflected them back, and then recombined them. If there was an ether wind, the light beam should have arrived back slightly out of phase, creating an interference pattern that would change as the Earth moved. They rotated their apparatus, and they measured with astonishing precision. The result? A resounding null. No matter how they oriented their experiment, no matter what time of year, they detected absolutely no difference in the speed of light. The ether, it turned out, did not exist. This was a profound statement about the nature of light itself. It meant that light doesn't need a medium to travel, and more importantly, it confirmed that the speed of light truly is constant for all observers, regardless of their relative motion. This was revolutionary, paving the way for Albert Einstein to propose something truly radical. Einstein, just 18 years after Michelson and Morley's experiment, took this constant speed of light as a fundamental postulate. He realized that if the speed of light must be constant for everyone, then our intuitive notions of space and time had to change. He proposed that space and time are not separate fixed entities but are instead interwoven into a single dynamic fabric called space-time. And it's within this fabric that the speed of light acts as an absolute unyielding speed limit. It's not that we can't go faster than light because our engines aren't powerful enough. It's that the very structure of space-time, the rules by which the universe operates, forbids it. As an object with mass approaches the speed of light, its effective mass increases, its length contracts, and time itself slows down for it relative to a stationary observer. To reach the speed of light, an object with mass would require infinite energy and experience time stopping entirely. These aren't just theoretical curiosities, they're observed, experimentally verified phenomena. The speed of light isn't a speed through space and time, it's the intrinsic speed of space and time itself. But what happens if we could somehow bypass this limit? That's when things get truly paradoxical, because breaking the light barrier isn't just about going fast. It's about fundamentally altering the relationship between cause and effect, between past, present, and future. To understand how that happens, we need to delve deeper into how this unyielding speed limit fundamentally twists our perceptions of time, leading us to the mind-bending concept of time dilation, which will be our focus in the next chapter. Welcome back, fellow cosmic voyagers. Last time we peered into the unyielding cosmic speed limit set by the constant speed of light, kick. We discovered it's not just a fast number, it's a fundamental principle woven into the very fabric of space-time. A principle so profound that breaking it wouldn't just mean getting somewhere faster, but fundamentally unraveling cause and effect itself. We promise to untangle how this unyielding speed limit twists our perception of time, leading us to the brink of paradox. And today, friends, we deliver on that promise. So let's dive headfirst into one of the most mind-bending consequences of Einstein's special relativity, time dilation. Imagine, if you will, a very special kind of clock. This isn't your grandfather's dusty old pendulum clock, nor is it the sleek digital one on your wrist. This is a light clock. Picture two perfectly parallel mirrors facing each other, with a single photon of light bouncing back and forth between them. Every time the photon hits one of the mirrors, that's one tick of our clock. Simple, right? The distance between the mirrors is fixed, and the speed of light is constant. So the time it takes for one tick is always the same. Now, let's play a thought experiment. A classic for a reason. Imagine you're standing perfectly still, holding this light clock. You observe the photon bouncing straight up and down, tick-tock, easy to follow. But what if that light clock, instead of being held by you, was on a super-fast spaceship zipping past you at an incredible relativistic speed, say 80% the speed of light? From your perspective, standing still on Earth, what would you see? This is where it gets wild. Remember our foundational principle: the speed of light is constant for all observers. Whether you're standing still or hurtling through space, light always travels at sea. This isn't a suggestion, it is a rigorously tested, experimentally confirmed fact. So as that spaceship with the light clock whizzes past you, the photon still has to travel from one mirror to the other at the exact same speed, chung-xi. But here's the kicker. Because the clock itself is moving horizontally, the light beam, from your stationary perspective, no longer travels straight up and down. Instead, it has to travel diagonally. It traces a longer zigzag path as it bounces between the moving mirrors. Think about it. By the time the photon reaches the top mirror, that mirror has moved forward a bit. So the light has to catch up, travelling at an angle. Now, let's put on our thinking caps. If the speed of light, our c, is constant and the light photon has to travel a longer distance in the moving clock compared to the stationary one, what does that mean for the time it takes? You got it. If the distance is longer and the speed is the same, then the time taken must be greater. From your stationary perspective, the light in the moving clock takes longer to complete one bounce. In other words, the moving light clock ticks slower than your stationary clock. And here's the truly mind-bending part. This isn't just an optical illusion. This isn't just the light looking like it's taking longer. The physical process of time itself is actually slowing down for the moving clock. This is time dilation. The faster you move relative to an observer, the slower your time appears to pass for that observer. Let that sink in for a moment. It's profoundly counterintuitive, isn't it? Our everyday Aquarius tells us time is universal, a steady, relentless march forward for everyone. But Einstein showed us that time is not an absolute fixed entity. It's relative, it's flexible, it's dynamic. This isn't just theoretical speculation either. We have real-world proof. Atomic clocks. In 1971, the Affel-Keating experiment flew atomic clocks around the world on commercial airliners. When compared to a stationary atomic clock on Earth, the clocks that had travelled at high speeds showed a slight but measurable difference. They had indeed ticked slower, just as predicted by special relativity. GPS satellites. This isn't just a fun fact, it's essential for modern technology. The GPS satellites orbiting Earth travel at high speeds, about 800 miles per hour, and experience time dilation. They also experience gravitational time dilation, a concept from general relativity we won't delve into today, but the point is, their clocks actually run slower by about 7 microseconds per day relative to clocks on Earth due to speed. If engineers didn't account for this relativistic effect, your GPS device would be off by several miles every single day. So time dilation is real. As an object approaches the speed of light, its time slows down dramatically from the perspective of a stationary observer. If you could somehow reach the speed of light, time for you would essentially stop. From an outside observer's perspective, you would be frozen in an eternal moment. Now, let's bridge this back to our central question. What happens if you try to go faster than light, FTL? If time slows down as you approach T-U and effectively stops at T, what would happen if you pushed beyond that limit? The mathematical equations of special relativity suggest something truly bizarre. If you could exceed the speed of light, time would begin to run backward for you, relative to a stationary observer. Think about the implications of that for a moment. If your time starts running backward, it means you could arrive at your destination before you even left your starting point. You could send a message that is received before it was sent. This isn't just futuristic, it's fundamentally paradoxical. This is the genesis of all the time paradoxes associated with FTL travel. The most famous example, of course, is the grandfather paradox. Imagine you build an FTL ship. You take off, accelerate past the speed of light, and travel back in time to an era before your grandparents met. What if you then, say, accidentally prevented their meeting? Or worse, intentionally caused some mischief that ensured they never had children? If your grandparents never met, your parent would never be born, and therefore you would never be born. But if you were never born, how could you have travelled back in time to prevent your grandparents from meeting in the first place? The paradox is a closed loop of logical impossibility. It breaks the fundamental law of causality, the principle that an effect cannot precede its cause. Every event in our universe follows a strict cause and effect relationship. The coffee spills because you knocked it over. You exist because your parents met. If FTL travel allows you to reverse time, even locally, it means you could create a situation where an effect happens before its cause, or where a cause is undone by its future effect. Let's consider a slightly less dramatic but equally illustrative FTL paradox. Imagine you're on Earth and your friend, an intrepid astrophysicist, is in an FTL ship. She sends you a message from her ship. If she's travelling faster than light, that message could theoretically arrive at Earth before. She even pushed the send button on her ship from your earthbound perspective. You receive the message, read it, and then, knowing its contents, you could send a warning back to her, telling her not to send the message in the first place. You've received a message that, because of your warning, was never sent. Again, a complete breakdown of cause and effect. This isn't a minor glitch the universe might overlook. This is a fundamental structural flaw. The universe, as we understand it, simply cannot allow such paradoxes to exist because they would unravel the very fabric of reality. Our experience of time as a linear progression, where cause always precedes effect, is deeply ingrained in the laws of physics. So why does going faster than light lead to time paradoxes? Because the constant speed of light isn't just a speed limit, it's the intrinsic speed of information, of interaction, and ultimately of causality itself. When you try to exceed K, you're not just breaking a speed barrier, you're trying to outrun cause and effect. You're trying to arrive at a destination before the journey has even begun, or affect an event before its cause has occurred. This isn't about having a faster engine or a more powerful fuel. This is about encountering a fundamental property of space-time. It's like trying to divide by zero. The laws of mathematics simply don't allow it, because it leads to nonsensical, undefined results. In physics, trying to go faster than light leads to nonsensical, undefined realities, realities where your own existence could be erased by your own actions. For many physicists, the fact that FTL travel inevitably leads to these logical paradoxes is strong evidence that it is simply impossible. The universe, in its elegant self-consistency, seems to have built in a fail-safe. The speed of light isn't just a barrier, it's a guardian, protecting the integrity of time and the inviolable order of cause and effect. So, while the dream of zipping across the cosmos in the blink of an eye remains a captivating one, the very architecture of our universe, dictated by the constant speed of light and the resulting time dilation, presents an unyielding theoretical blockade. It forces us to confront the reality that to travel faster than light is to travel into a realm where time itself ceases to make sense, where the past, present, and future become hopelessly intertwined in a tapestry of contradictions. But what if there's a loophole? What if there are ways to circumvent the speed limit without breaking it locally? That, my friends, is a question for another time, perhaps another chapter. For now, let's marvel at the sheer elegance and strictness of a universe where time itself is relative and where a simple constant holds the key to the very nature of reality. If you're enjoying this journey through the mind-bending cosmos with us at Dreamy Science, I'd love it if you'd hit that like button and subscribe. It helps us bring more of these fascinating explorations to life. And as always, share your thoughts in the comments below. Does the idea of time dilation make intuitive sense to you now, or is it still a cosmic head-scratcher? I'm always curious to hear your perspectives. Next time, we'll continue our exploration of space-time, perhaps venturing into the strange world of wormholes and warp drives, and asking if there are any theoretical pathways to distant stars that don't involve breaking the cosmic speed limit and inviting temporal chaos. Stay curious and keep dreaming big. Welcome back to Dreamy Science, fellow cosmic explorers. If you've been with us since the beginning, you know we've grappled with one of the universe's most unyielding truths. The speed of light is an absolute constant and unbreakable cosmic speed limit. We've seen how trying to push a massive object to suck would require infinite energy, and how exceeding it mathematically suggests time would run backward, unraveling the very fabric of causality with mind-bending paradoxes like the grandfather paradox. But what if there was a loophole? What if we could circumvent this cosmic speed limit without actually breaking it? This isn't about pushing a spaceship through space faster than light. It's about manipulating the very fabric of space-time itself to bring distant points closer, or to move space around us. Today, we're diving into the realm of theoretical physics, where the impossible might just become merely improbable. We're talking about warp drives and wormholes. First, let's tackle the concept of a warp drive. When we imagine starships zipping across galaxies in science fiction, often what we're seeing is some form of warp drive in action. The most famous theoretical model is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, and here's the truly fascinating part. It doesn't violate Einstein's theory of relativity locally. Think of it this way. Imagine you're standing on a moving sidewalk at an airport. You can walk on that sidewalk, and relative to the ground, you're moving much faster than if you were just walking. But relative to the sidewalk itself, you're still just walking at your normal pace. You haven't broken any personal speed limits, you've simply used the moving sidewalk to your advantage. The Alcubierre drive works on a similar, albeit far more cosmic principle. Instead of moving through space, it proposes to move space itself. Picture a spaceship encased in a warp bubble. This bubble would compress the space-time in front of the ship, effectively shortening the distance to its destination. Simultaneously, it would expand the space-time behind the ship, pushing it forward. The ship itself, inside this bubble, would remain essentially stationary or move at a sublight speed relative to its immediate surroundings. It's like being on a surfboard, riding a wave of distorted space-time. So the key here is that nothing inside the warp bubble actually travels faster than light. The ship isn't accelerating to impossible speeds. Instead, the universe is being squished and stretched around it. This means that in theory, local causality is preserved. You're not arriving before you left in your local frame of reference. The light from your destination would still reach you within your bubble. The incredible journey in this framework happens because the path itself is being manipulated. This sounds like a perfect solution, right? A way to travel to distant stars without falling into the black hole of time paradoxes. Well, not so fast. While mathematically consistent with Einstein's field equations, the Alcubierre drive comes with a monumental catch. It requires exotic matter. What is exotic matter? It's not just some rare element from a distant nebula. In this context, exotic matter refers to matter with negative energy density. Normal matter, like everything you and I are made of, has positive energy density and creates gravity, pulling things together. Exotic matter, on the other hand, would have properties that allow it to repel gravity, or effectively create negative mass. It's this negative energy density that would be needed to create the warp bubble, to compress space in front and expand it behind. And here's the problem. We have never observed exotic matter. While general relativity doesn't strictly forbid its existence, it's a concept that pushes the boundaries of our current understanding of physics. Creating enough of it and controlling it with the precision required is currently far beyond our technological capabilities, perhaps even fundamentally impossible. So while the Alcubierre drive offers a fascinating theoretical pathway to faster-than-light travel that might sidestep paradoxes by not locally exceeding Q, its practical realization remains firmly in the realm of science fiction for now. Now let's shift our gaze to another mind-bending concept that offers shortcuts across the cosmos: wormholes. If warp drives are about surfing space-time, wormholes are about punching a hole through it. Imagine you have a piece of paper and you draw two dots on it far apart. To get from dot A to dot B, you have to travel across the paper. That's like travelling through normal space. But what if you fold the paper so that dot A and dot B are directly on top of each other? Then you could theoretically just poke a pencil through the paper, creating a direct connection, a shortcut. That's the essence of a wormhole, also known as an Einstein-Rosen bridge. It's a theoretical tunnel through space-time that connects two incredibly distant points, or even different points in time, or perhaps even different universes. Instead of travelling the vast distances between stars, you could theoretically step into one end of a wormhole and instantaneously emerge at the other, light years away. Again, like the warp drive, a wormhole doesn't require you to travel faster than light within the tunnel itself. You're just taking a shortcut. The speed of light is still the local speed limit within the wormhole's throat. The faster-than-light aspect comes from the fact that you traverse an immense astronomical distance in an incredibly short amount of time, much less time than light would take to travel the conventional path. So what does it take to create or stabilize a wormhole? Unsurprisingly, it also requires our old friend exotic matter with negative energy density. Without it, any theoretical wormhole would be incredibly unstable, collapsing faster than light could even cross it. it would be a fleeting microscopic phenomenon, utterly useless for interstellar travel. The exotic matter would act as scaffolding, propping open the wormhole's throat, allowing objects to pass through. But here's where wormholes take a truly perilous turn back into our discussion of time paradoxes. Unlike the Alcubierre drive, which is generally designed to avoid backward time travel, wormholes have a much stronger, more direct theoretical link to it. Remember our discussion about bedtime dilation from Chapter 2? The idea that time slows down for an object in motion relative to a stationary observer? Well, imagine you have a stable wormhole. Now, take one end of that wormhole and accelerate it to nearly the speed of light, then bring it back to its starting point. Because of time dilation, the accelerated end of the wormhole would have experienced less time than the stationary end. Let's say you take one end of a wormhole, put it on a spaceship and send that spaceship on a relativistic journey for what feels to the ship like a few days, but to Earth it's decades. When the ship returns, one end of the wormhole is now decades younger in its internal clock than the other end. What does this mean? It means if you step into the older end of the wormhole, you could emerge from the younger end in the past, relative to the older end's timeline. You could effectively travel backward in time, and with backward time travel, all those dizzying paradoxes we explored come rushing back. The grandfather paradox is no longer a theoretical exercise confined to FTL travel. It becomes a very real possibility. If you could step through a wormhole and arrive in your past, what would stop you from altering events that led to your own existence? What about sending a message to yourself before you even thought of the question? The FTL message paradox. In a new guise, the very fabric of cause and effect, the fundamental principle that an effect must follow its cause, would be utterly shattered. This is why many physicists are deeply skeptical about the practical existence of traversable wormholes that allow for time travel. The universe, in its elegant self-consistency, seems to have built-in safeguards. The need for exotic matter, the inherent instability, and the potential for causality violations all point to the idea that these cosmic shortcuts, while tantalizing, might be fundamentally impossible, or at the very least so incredibly difficult to achieve that they remain forever out of reach. So while warp drives and wormholes offer intriguing theoretical possibilities for interstellar travel, they don't necessarily offer an easy escape from the universe's unyielding laws. The speed of light, Gauss, remains the ultimate guardian of causality. Even when we try to manipulate space-time itself, the ghost of paradoxes, particularly with wormholes, seems to haunt these theoretical constructs. They remind us that the universe is not just about speed and distance, it's about the fundamental relationships between space, time, energy, and cause and effect. Are we truly stuck in our cosmic neighborhood, forever bound by the speed of light? Or are these theoretical ideas just the first whispers of a physics we don't yet fully comprehend? A new understanding that might unlock the stars without breaking the universe? I'm always curious to hear your thoughts on these mind-bending concepts. Do you think humanity will ever find a way to traverse the stars using warp drives or wormholes? Let us know in the comments below. If you're enjoying this journey through the universe's most astounding secrets, I'd love it if you'd hit that like button and subscribe to Dreamy Science for more explorations into the wonders of our cosmos. Join us next time as we dive even deeper into the philosophical implications of time travel and the very nature of reality itself. Until then, keep looking up and keep dreaming big, because the universe is full of mysteries waiting to be uncovered. Welcome back to Dreamy Science, where we're not just exploring the physics of the universe, but diving headfirst into the very fabric of reality itself. In our last chapter, we ventured into the tantalizing possibilities of warp drives and wormholes, those theoretical shortcuts through space-time that promise to circumvent the unyielding cosmic speed limit without locally breaking it. But as we discovered, even these ingenious concepts carry a heavy burden. Warp drives demand exotic matter, a substance as elusive as a unicorn. And wormholes? Those cosmic tunnels, while offering tantalizing routes across vast distances, come with a mind-bending caveat. They open a direct, undeniable pathway to backward time travel. And with backward time travel, my friends, we're dragged right back to the precipice of those terrifying, reality-unraveling time paradoxes. The speed of light isn't just a physical barrier. It appears to be a cosmic censor, a guardian of causality itself. It prevents us from ever reaching the speeds that would allow us to witness effects preceding their causes, to fundamentally rewrite the past. But what if, just for a moment, we imagine a universe where such travel is possible? What the philosophical implications of a reality where the past isn't fixed, where cause and effect can be swapped like playing cards? This isn't just a physics problem. It's a profound question about the nature of existence, free will, and the very consistency of time. Let's revisit our old friend, the grandfather paradox. You travel back in time, accidentally or intentionally, and prevent your grandparents from meeting. If they never meet, they never have children, one of whom is your parent. If your parent is never born, then you are never born. But if you're never born, how could you have gone back in time to prevent your grandparents from meeting in the first place? It's a logical knot, a self-cancelling loop that screams impossible at the very structure of our understanding. This isn't just a fun mental exercise. It strikes at the heart of our perception of reality. If such a paradox could occur, it implies a fundamental inconsistency in the universe. It suggests that reality itself could unravel, that the very sequence of events that defines our existence could be erased or rewritten. The universe, as we experience it, is built on an unbreakable chain of cause and effect. Every action has a reaction, every event a preceding cause. Time travel that allows for paradoxes shatters this chain, leaving us in a state of utter conceptual chaos. So if time travel were truly possible, how could the universe prevent these paradoxes from occurring? This is where philosophers and theoretical physicists have offered some truly mind-bending solutions, each with its own profound implications for the nature of time itself. One popular idea is the Novikov self-consistency principle. Named after Russian astrophysicist Igor Novikov, this principle suggests that the universe is inherently self-consistent. Any actions taken by a time traveler, no matter how seemingly disruptive, would always lead to an outcome that is consistent with the original timeline. In essence, you simply cannot change the past. Imagine you travel back in time to prevent a catastrophic event. According to Novikov, one of two things would happen. Either you would fail in your attempt, perhaps your time machine malfunctions, or you're simply too late. Or even more subtly, your actions would somehow become the very cause of the event you were trying to prevent, or they would lead to the exact same outcome through a different path. Your attempt to change the past would, paradoxically, ensure its occurrence. Consider the grandfather paradox again through this lens. If you tried to prevent your grandparents from meeting, the Novikov principle suggests you would inevitably fail. Perhaps you'd get stuck in a traffic jam, or you'd accidentally introduce them yourself, or your actions would simply have no effect on their eventual meeting. The timeline in this view is like a river that must reach the sea. You can throw rocks in it, try to divert it, but its ultimate course is fixed. This perspective suggests a deterministic universe, where free will, at least concerning the past, is an illusion. You're free to act, but your actions will always conform to the pre-existing history. It's a humbling thought, isn't it? That the past is an unchangeable tapestry, and we are merely threads within it, unable to snip or reweave. But what if there's a different way to resolve paradoxes, one that doesn't strip us of our agency? Enter the fascinating and equally controversial but many worlds interpretation of quantum mechanics. While not originally conceived to explain time travel, it offers a compelling framework for resolving paradoxes. In this view, every single quantum event, every decision, every possibility causes the universe to split into multiple parallel realities. If you were to travel back in time and prevent your grandparents from meeting, you wouldn't erase your own existence. Instead, your actions would simply create a new parallel universe, a branching timeline where your grandparents never met, and you as a result were never born in that specific branch. Your original timeline, the one you came from, would remain perfectly intact and unchanged. You would effectively be jumping from one branch of reality to another. Think of it like this. You're reading a choose-your-own-adventure book. When you make a choice, you turn to a specific page. But in the many worlds interpretation, every choice you could have made also leads to a new, equally real book, continuing the story in a different direction. Time travel, then, isn't about changing the past, but about creating a new future by stepping into a different branch of reality. This elegantly sidesteps paradoxes because the original timeline is never altered. The grandfather paradox becomes moot. You simply become the grandfather of a different timeline, leaving your original one untouched. This interpretation is profoundly liberating in some ways, suggesting an infinite multiverse where every possibility, no matter how small, is realized in some corner of existence. But it's also incredibly humbling, implying that our reality is just one of an infinite number of parallel streams, and that every decision we make spawns countless versions of ourselves. These philosophical approaches force us to confront the very nature of time itself. Is time a flowing river, where only the present is real and the past is gone forever while the future is yet to be written? This is often called presentism. Or is time more like a fixed four-dimensional block, where past, present and future all exist simultaneously, like frames in a cosmic film reel? This is known as eternalism, or the block universe theory. If the block universe theory is correct, then time travel wouldn't be about changing the past, but simply about navigating to a different location within this fixed block of space-time. You wouldn't be altering anything. You'd simply be observing or experiencing a different part of the existing reality. This aligns beautifully with the Novikov self-consistency principle, as any journey into the past would simply be part of the preordained, self-consistent structure of the block. There's no changing a fixed film reel, only playing it back from a different point. So we come full circle, don't we? The unyielding cosmic speed limit key isn't just a physical law. It stands as a sentinel at the gateway of these profound philosophical questions. Whether the universe is self-consistent and deterministic, or an ever-branching multiverse, the very fabric of reality seems to be protected from the chaos of true, paradox-inducing time travel. The speed of light, this seemingly simple constant, acts as the ultimate cosmic sensor, preventing us from ever reaching those speeds that would shatter causality and plunge us into a realm where effects precede causes, where our very existence could be undone. Without the speed of light as this guardian, The universe as we know it, with its predictable cause and effect relationships, its linear progression of events, and even our sense of a coherent personal history, would fall apart. It would be a universe of infinite possibilities, yes, but also one of infinite contradictions, where nothing could truly be said to have happened, because it could always be undone. The implications are breathtaking. It means that the universe, in its fundamental design, prioritizes order, consistency, and the preservation of causality above all else. The impossibility of faster-than-light travel isn't a limitation. It's a profound protection. It ensures that the story of the universe, our story, unfolds in a coherent, logical sequence, even if that sequence contains mysteries that continue to humble and astound us. As we conclude this deep dive into the mind-bending consequences of faster-than-light travel and its intimate link to time paradoxes, we're left with a sense of awe. The speed of light isn't just a number, it's a fundamental pillar of reality, upholding the very structure of time and space and safeguarding the causal integrity of the cosmos. It's a reminder that sometimes the greatest wonders of the universe lie not in breaking the rules, but in understanding the profound elegance and necessity of the rules that govern all existence. If you've enjoyed this journey through space-time causality and the deepest philosophical questions about reality, please hit that like button, subscribe to Dreamy Science, and share your thoughts in the comments below. What do you think about the nature of time? Is the universe deterministic, or does it branch into infinite possibilities? I'm always curious to hear your perspectives on these mind-bending topics. Join us next time as we reflect on our entire journey and consider what these cosmic limits truly mean for humanity's place in the universe. Welcome back to Dreamy Science. We've journeyed through some truly mind-bending concepts over the past few chapters, haven't we? We've seen how the unyielding cosmic speed limit of light isn't just a number, but a fundamental guardian of causality, protecting the very fabric of our reality from the chaos of time paradoxes. We've wrestled with the implications of time dilation, pondered the theoretical possibilities of warp drives and wormholes, and even delved into the philosophical depths of the Novikov self-consistency principle and the many worlds interpretation. Now, as we stand at the threshold of our final chapter, let's take a moment to reflect on what all of this truly means. What do these cosmic limits, these profound protections, signify for us, for humanity, and for our place in this astonishing universe? Think about it. The speed of light isn't just a barrier, it's a cosmic sensor, as we discussed. It dictates the size of our observable universe, the reach of our messages, and perhaps most profoundly, the very definition of now across vast cosmic distances. If you were to look at a galaxy millions of light years away, you're not seeing it as it is right now, but as it was millions of years ago. That's not just a cool fact. It's a profound statement about the interconnectedness of space and time, and the fundamental limitations on our perception of simultaneity. This can feel confining, can't it? To know that the stars, the nebulae, the countless other worlds we glimpse through our telescopes are forever beyond the reach of conventional travel within a single human lifetime. It's a sobering thought, a stark reminder of our cosmic humility. But is it truly a limitation, or is it perhaps a profound protection, a cosmic embrace that ensures a coherent, stable universe for us to inhabit and explore? I'd argue it's both. The universe, in its infinite wisdom, seems to have built-in safeguards. The very laws of physics, which allow for the breathtaking beauty of galaxies and the intricate dance of planets, also prevent us from unraveling causality. It's a universe that makes sense, a universe where cause precedes effect, where the past is fixed and the future is, at least in part, unwritten. And that, my friends, is a truly precious thing. Yet humanity's spirit is one of insatiable curiosity and relentless exploration. We look at the stars, and we don't just see limits, we see challenges. We see the next frontier. And this brings us to one of the most exciting and perhaps most speculative aspects of our journey. The possibility of a physics we don't yet fully comprehend. You see, while special relativity and general relativity are incredibly robust, experimentally verified theories, they aren't necessarily the final word. Science is an ongoing conversation, a continuous process of discovery and refinement. What if there are deeper layers to reality, fundamental principles we haven't yet uncovered that could offer a different path to the stars? Imagine for a moment a paradigm shift so profound it redefines our understanding of space, time, and matter. We've talked about exotic matter, the theoretical substance with negative energy density required for warp drives and stable wormholes. Currently, this remains firmly in the realm of speculation. We've never observed it, nor do we fully understand how it could be created or manipulated. But what if it exists? Or what if there's an entirely different way to achieve its effects? Consider the strange world of quantum mechanics. Here, particles can be entangled, meaning they are linked in such a way that the state of one instantaneously influences the state of the other, no matter how far apart they are. This phenomenon, famously dubbed spooky action at a distance by Einstein, seems to defy our classical understanding of locality and speed limits. However, and this is a crucial distinction, entanglement doesn't allow for faster-than-light information transfer. You can't use it to send a message to the past or future, or to a distant galaxy faster than light. The information needed to decode the entangled state still travels at sec. But what if there's more to quantum mechanics than we currently grasp? What if the universe isn't just 3 spatial dimensions and 1 time dimension? String theory, for instance, postulates the existence of extra spatial dimensions, curled up so tightly that we don't perceive them. Could these hidden dimensions offer shortcuts, or perhaps even a different way to navigate the cosmos that bypasses the limitations of our familiar spacetime? This is where the true dreamy science comes into play. We're talking about concepts that are at the very edge of theoretical physics, ideas that require breakthroughs on the level of Einstein's revolution, or even beyond. It's not just about finding a new particle, it's about discovering entirely new properties of space-time, new ways that energy and matter interact, or even new laws of physics that emerge under extreme conditions we can only theorize about. Perhaps the exotic matter isn't a substance we can physically create in a lab, but a manifestation of some deeper property of the vacuum itself, something we could learn to manipulate with an advanced understanding of quantum gravity. What if gravity, the very force that shapes the cosmos, holds secrets about manipulating space-time that we have only just begun to uncover? This isn't about disproving Einstein, it's about building upon his monumental work, pushing the boundaries of our knowledge. It's about asking the what-if questions that drive scientific progress. What if the universe is far stranger, far more intricate than our current models suggest? What if the cosmic censor isn't an absolute prohibition, but a temporary measure, a lock that can be picked with the sufficiently advanced understanding of the universe's deepest secrets? Of course, the immediate implications of any FTL travel, even if achieved through an entirely new physics, would still need to contend with the causality paradoxes we've explored. If you can travel faster than light, you can by definition travel into your own past. So even if a new physics allows us to bypass peak locally, the universe would still need a mechanism to uphold causality, perhaps one of the principles we've discussed. or something entirely new. The universe seems to have a deep aversion to paradoxes, so where does this leave us? It leaves us in a state of wonder, of boundless curiosity. It leaves us with the understanding that the universe is both incredibly elegant in its laws and astonishingly mysterious in its depths. The unyielding speed limit of light, far from being a cosmic prison, is actually a cosmic architect, shaping a reality that is coherent, predictable, and ultimately habitable. It ensures that the story of the universe unfolds in a logical, step-by-step manner. But it also leaves us with the tantalizing possibility that our current understanding is just a chapter in a much larger, epic saga. The journey of scientific discovery is never truly finished. We may not have faster than light travel today or even tomorrow, but the human spirit of inquiry, the drive to understand, to explore, to push the boundaries of what is known, that, my friends, is what truly allows us to reach for the stars, even if it's one light year at a time. For now, the vastness of the cosmos, with all its unfathomable beauty and terrifying distances, remains largely beyond our physical grasp. But it is not beyond our imagination, our curiosity, or our scientific endeavour. We continue to explore it with our telescopes, our probes, and most importantly with our minds. We delve into the mysteries of dark matter and dark energy, the origins of the universe, and the search for life beyond Earth, all within the bounds of the cosmic speed limit. And there, within those bounds, lies an infinite universe of discovery. So, as we conclude this season of dreamy science, let's carry with us not just the facts about time dilation, but also a renewed sense of awe for the universe's intricate workings. Let's appreciate the elegant simplicity of its fundamental laws, even when they present us with mind-bending paradoxes. And let's never stop dreaming, never stop asking what if, and never stop pushing the boundaries of what we believe is possible, because that, after all, is the essence of science. If you've enjoyed this journey through the cosmos and the mysteries of time, I'd love it if you'd hit that like button, subscribe to Dreamy Science, and share your thoughts in the comments below. What do you think about the cosmic speed limit? Is it a barrier or a blessing? And what new physics do you dream of discovering? I'm always curious to hear your perspectives. Until next time, keep looking up, keep questioning, and keep dreaming big. This is Dreamy Science, signing off. Welcome back to Dreamy Science, where we journey through the cosmos, not just to understand its laws, but to marvel at their elegant necessity. In our last chapter, we wrapped up our deep dive into the universe's most unyielding cosmic speed limit, the speed of light, Cool. We explored how it acts as a cosmic embrace, a fundamental constant that ensures a coherent, stable reality, protecting the very fabric of causality from the unravelling threads of time paradoxes. We talked about humanity's insatiable curiosity, our enduring dream of reaching the stars, and the tantalizing, perhaps even revolutionary possibility of a new physics that might one day offer pathways to interstellar travel without violating the universe's profound aversion to paradoxes. But what is this new physics we speak of? Is it merely a hopeful whisper in the dark, or are there genuine frontiers of discovery that could redefine our understanding of space, time, and causality itself? Today we're going to lean into that mystery, peering into the theoretical realms where the universe might just be holding more secrets than we currently grasp. Remember how we've stressed that the universe doesn't bend its rules, but rather so we might not yet fully comprehend them. That's the crux of this new physics discussion. It's not about finding a loophole to cheat the speed of light. It's about discovering a deeper, more fundamental layer of reality, where what we perceive as FTL travel might actually be something else entirely, something that inherently respects causality. Imagine for a moment that our current understanding of space-time as described by Einstein's general relativity is like a beautifully rendered 2D map of a vast, complex 3D world. The map is incredibly accurate for navigation on the surface, but it doesn't show you the mountains, the valleys, or the tunnels that might exist through those mountains. We can travel across the surface, but we might be missing entire dimensions of movement or connection. One of the most exciting and indeed mind-bending areas where this new physics might emerge is in the quest for quantum gravity. This is the holy grail of theoretical physics, an attempt to unify two of our most successful yet seemingly incompatible theories: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the incredibly tiny world of particles and forces. Right now, these two frameworks don't play nicely together. General relativity sees space-time as a smooth, continuous fabric, while quantum mechanics suggests that everything, even space and time themselves, might be granular, quantized at the smallest scales. If space-time isn't truly continuous, if it's made up of discrete chunks or pixels, what does that mean for our journey through it? Think about it. If you zoom in close enough on a digital image, you eventually see the individual pixels. Could the smooth space-time we experience simply be an emergent property of something far more complex and fundamentally different at the Planck scale? That unbelievably tiny scale where quantum effects dominate gravity. Theories like loop quantum gravity or string theory are attempting to bridge this gap. String theory, for instance, posits that fundamental particles aren't point-like but rather tiny, vibrating strings. And here's where it gets truly wild. For string theory to work mathematically, it often requires the existence of extra spatial dimensions, the dimensions beyond the three we perceive: up, down, left, right, forward, backward, and the one dimension of time. Now, before you think we've completely lost our minds, these extra dimensions aren't necessarily places you can just step into like another room. They might be compactified or curled up into incredibly tiny spaces, too small for us to detect directly with current technology. Picture a garden hose. From far away, it looks like a 1D line, but if you zoom in, you see it has a second curled up dimension around its circumference. What if our universe is like that, with several dimensions curled up so tightly we don't even perceive them? If these extra dimensions exist, what if they offer entirely new pathways through space-time? What if instead of traversing vast cosmic distances within our familiar 3 dimensions, we could somehow leak or tunnel through one of these hidden dimensions, effectively taking a shortcut that bypasses the whole limit in our perceived reality? This isn't about going faster than light locally in our 3D space. It's about finding a different route that makes the journey appear instantaneous or superluminal from our perspective, without ever violating the light speed limit in the local higher dimensional space. This is where the concept of brains comes into play in some theories, the idea that our entire universe, with all its stars and galaxies, might just be a 3D brain floating within a higher dimensional bulk. If we could somehow manipulate our brain or interact with the bulk, perhaps we could achieve what appears to be FTL travel. The distance between 2 points in our 3D universe might be immense, but in the higher dimensions, those 2 points might be right next to each other. It's like folding a piece of paper to bring 2 distant points together. Except here, the folding happens in dimensions we can't normally access. But the question remains, even if we find these shortcuts, how do they avoid time paradoxes? This is where the universe's aversion to paradoxes comes back into play, but perhaps in a more sophisticated form. If a new physics allows for what appears to be FTL travel, it must inherently be a form of travel that doesn't allow for true backward time travel in a way that generates paradoxes. Consider this. Perhaps the very nature of time itself is more complex than our linear past, present, future perception. What if time at a fundamental level isn't just a river flowing in one direction, but a more intricate structure where cause and effect are always intrinsically linked, regardless of our perceived speed? For instance, if these extra dimensions or quantum gravity effects allow for FTL equivalent travel, it's possible that they also inherently enforce a cosmic self-consistency. This isn't just the Novikov principle as a rule that prevents paradoxes, it's a fundamental property of the universe's architecture. Maybe the new physics reveals that while you can take a shortcut across the universe, the very fabric of reality prevents you from ever arriving. Before you left, no matter how clever your shortcut. The universe, in its deep wisdom, might have built-in safeguards, not just against local FTL, but against any manipulation of space-time that would unravel causality. This could mean that any shortcut through higher dimensions or quantum foam would still respect the overall causal structure of the cosmos. You might arrive at a distant galaxy in what feels like an instant, but that instant is still after you departed from a universal perspective. The faster-than-light effect would be an illusion of speed within our 3D perception, not a violation of the fundamental arrow of time. Another fascinating thought experiment often arises when we consider the nature of time. What if time isn't a fundamental entity but an emergent one, like temperature or pressure? If that were the case, a new physics might reveal how to manipulate the conditions that give rise to our perception of linear time, allowing for a different kind of temporal experience without ever truly going back in time to alter events. It's a subtle distinction, but a crucial one for causality. You wouldn't be changing the past. You'd be experiencing time in a way that bypasses our usual linear progression. This is where the cosmic sensor hypothesis, which we discussed earlier, takes on a grander, more elegant form. Instead of Q being the sole sensor, perhaps the universe itself, through its as-yet undiscovered laws, has an even more profound mechanism to protect its integrity. It's not just a speed limit, it's a causal firewall that operates at every level of reality, from the smallest quantum fluctuation to the largest cosmic structure. Any new physics that allows for interstellar travel would have to operate within the confines of this causal firewall, not outside it. So, what does this mean for us, the curious explorers of dreamy science? It means the journey of discovery is far from over. Our current models of the universe are incredibly powerful and accurate, but they are, by definition, models. They are our best attempt to describe reality based on what we've observed and tested. But science is always evolving, always pushing the boundaries of what's known. The human drive to explore, to understand, to reach beyond our current grasp is an engine of progress. It's what pushes us to build larger telescopes, more powerful particle accelerators, and to dream up theories that challenge our most fundamental assumptions. The dream of interstellar travel isn't just about getting from point A to point B. It's about expanding our consciousness, about asking profound questions about our place in the universe, and about discovering if life exists beyond Earth. If a new physics truly emerges, one that allows for FTL-equivalent travel without unraveling causality, it would represent a revolution in human understanding akin to the Copernican or Einsteinian revolutions. It would fundamentally change our understanding of space, time, and perhaps even our very existence. The universe would no longer feel quite so vast and isolating, and the stars would transform from distant pinpricks of light into potential destinations. But even with such a profound shift, the core lesson of our journey through Hoxk and causality would remain. The universe is elegant, self-consistent, and profoundly logical, even when that logic is counterintuitive to our everyday experience. It sets the rules, and if we are to achieve our dreams of interstellar voyaging, it will be by understanding those rules more deeply, not by breaking them. We won't be outsmarting the universe, we'll be finally understanding how it works at a level we can barely imagine today. This exploration into new physics is a testament to the fact that science is not static. It's a dynamic, ongoing conversation with the cosmos. We start with what we know, we test our assumptions, and when those assumptions break down, or when new phenomena emerge, we build new frameworks, new understandings. The very questions we're asking about FTL travel and time paradoxes are pushing us towards those new frontiers, forcing us to consider possibilities that once seemed like pure fantasy. So as we bring this particular series on the speed of light and time paradoxes to a close, remember this: the universe is a place of profound wonder and mystery. The speed of light isn't just a barrier, it's a guidepost directing us towards a deeper understanding of reality's fundamental laws. Whether humanity will ever achieve interstellar travel in a way that satisfies our yearning yet preserves causality remains the greatest scientific and philosophical puzzle of our time. But the pursuit of that answer, the very act of asking these questions, is what makes us truly human. It's what makes us explorers, dreamers, and scientists. What are your thoughts on this new physics? Do you believe there are hidden dimensions or deeper aspects of time waiting to be discovered? Or do you think Siu will forever remain the ultimate cosmic barrier, ensuring our universe remains a causally consistent, albeit vast, place? Let us know in the comments below. Your insights are what make dreamy science truly special. If you've enjoyed this mind-bending journey through the cosmos with us, I'd love it if you'd hit that like button and subscribe to Dreamy Science. And don't forget to ring that notification bell so you don't miss our next deep dive into the wonders of the universe. Until then, keep looking up, keep asking questions, and keep dreaming big. This is Dreamy Science, signing off for now, but our exploration of the universe's grand mysteries is far from over. Welcome back to Dreamy Science, fellow cosmic explorers. Last time we left you with a tantalizing idea, a concept that sits at the very heart of why faster-than-light travel seems so stubbornly out of reach. The universe itself might possess a causal firewall. It's an inherent, almost elegant mechanism designed to protect the very fabric of reality from the kind of temporal paradoxes that FTL travel, in its simplest interpretation, would unleash. But what exactly is this firewall? How does it operate? And does it truly make the impossible, well, truly impossible? Today we're diving deeper into this profound concept, exploring the universe's apparent insistence on self-consistency and what that means for our dreams of interstellar travel. Imagine, if you will, the universe as an incredibly complex self-regulating system. Every event, every action, every interaction is a node in an intricate network of cause and effect. A causes B, B causes C, and so on. This isn't just a convenient way to describe reality, it's fundamental to how we understand and experience existence. If you drop a ball, it falls. If you flip a switch, a light turns on. These are simple everyday demonstrations of causality. Now, picture a scenario where you could travel faster than light. As we've explored, the equations of special relativity suggest that exceeding King would mean travelling backward in time relative to some observers. And if you can travel backward in time, you can theoretically arrive before you left. This is where the causal firewall kicks in. Let's revisit the classic grandfather paradox. You build your FTL ship, jump through time, and arrive in the past where you somehow prevent your grandparents from meeting. Presto! Your parents are never born, which means you are never born. But if you were never born, how could you have built the FTL ship and gone back in time to prevent your own birth? See the problem? It's a logical short circuit, a cosmic error message that screams system failure. The causal firewall, then, is not a physical wall you can bump into. It's a conceptual boundary, an intrinsic property of space-time itself that seems to prevent such logical inconsistencies from ever arising. It suggests that the universe has an unbreakable rule: causality must always be preserved. The effect can never precede its cause. The past must remain immutable, at least from the perspective of an event that originates in the future. This isn't just a philosophical musing, it's deeply embedded in our most successful physical theories. Special relativity, while not explicitly designed to prevent paradoxes, inherently does so by setting as the ultimate speed limit. General relativity, which describes gravity as the curvature of space-time, also contains solutions that could allow for closed time-like curves, CTCs, paths through space-time that lead back to their starting point in time. Wormholes, for instance, are one theoretical pathway to CTCs. However, every time physicists try to make these CTCs physically realistic, they run into insurmountable problems, often requiring conditions that seem impossible, like infinite amounts of exotic matter or violations of fundamental energy conditions. It's almost as if the universe, in its elegant design, has an internal paradox prevention protocol. If a theoretical pathway to FTL or time travel emerges from our equations, the universe seems to throw up a series of physical roadblocks. Perhaps exotic matter, with its negative energy density, is simply impossible to create or sustain in sufficient quantities. Perhaps wormholes, while mathematically valid, are inherently unstable or collapse instantly upon formation, preventing any macroscopic object from traversing them. These aren't just practical engineering challenges, they might be fundamental limitations woven into the very fabric of reality. Think of it like this: you're playing a video game, and there's a specific area the developers don't want you to access. Instead of an invisible wall, they might make the ground too slippery to walk on, or the air too thin to breathe, or simply have the game crash if you try to glitch through. The universe, in its infinite wisdom, might be employing similar, albeit far more sophisticated mechanisms to safeguard its timeline. This exact puzzle led to profound theoretical concepts like Stephen Hawking's chronology protection conjecture. This conjecture posits that the laws of physics are such that they prevent macroscopic objects from ever forming closed time-like curves. In simpler terms, the universe hates time travel paradoxes so much that it actively finds ways to shut down any possibility of them occurring. It's not just that we haven't figured out how to travel faster than light or backward in time, it's that the universe itself might be intrinsically structured to prevent us from ever doing so in a way that would break causality. This isn't a limitation born of malice, but of necessity. Without a stable, consistent timeline, the entire universe unravels. If effects could precede causes, then the very notion of scientific predictability, of physical laws, would crumble. It would be a chaotic, nonsensical existence where anything could happen and nothing would make sense. Our ability to observe, measure, and understand the universe relies on this unwavering adherence to causality. So if the speed of light is an unyielding cosmic speed limit, and if wormholes and warp drives, while theoretically possible, seem to run into these causal firewall issues, where does that leave our human drive for exploration? Are we forever confined to the relatively slow pace of sublight travel, patiently waiting for light years to pass? This is where the idea of new physics truly becomes fascinating. The causal firewall isn't necessarily an absolute no to all forms of superluminal travel, it's a no to forms of superluminal travel that break causality. The challenge then is to find a way to circumvent the local speed limit of light without violating the cosmic principle of causality. Our current understanding of physics, while incredibly successful, is incomplete. We know that general relativity, which describes the universe on large scales, breaks down at the quantum level. We also know that quantum mechanics, which describes the universe on small scales, doesn't easily reconcile with gravity. This fundamental disconnect is one of the biggest mysteries in modern physics. Enter the quest for a unified theory, or a theory of quantum gravity. This is where brilliant minds are exploring ideas like string theory, M-theory, and loop quantum gravity. These theories aim to describe gravity and all other fundamental forces within a single, coherent framework, often by proposing that space-time itself isn't a smooth continuous fabric, but something granular, foamy, or even made of tiny vibrating strings or loops at the Planck scale, an unimaginably small scale. What if within these deeper, more fundamental descriptions of reality, there are new ways to manipulate space-time that we haven't even conceived of yet? What if our current understanding of space-time is like looking at a calm ocean surface, when beneath it lies a churning, complex network of currents and depths? A truly unified theory might reveal hidden dimensions or a deeper structure to space-time that allows for shortcuts or faster travel, without locally exceeding and without violating causality. Imagine for a moment that space-time isn't just a 3D arena for objects to move through, but a dynamic, multi-dimensional entity. String theory, for instance, postulates the existence of extra spatial dimensions, perhaps as many as 10 or 11, that are currently curled up or compactified at incredibly small scales, making them imperceptible to us. If these dimensions could be accessed or manipulated, perhaps they could offer a pathway around the causal firewall, not by breaking it, but by finding a higher dimensional workaround. This isn't science fiction anymore, at least not entirely. These are serious avenues of research for physicists trying to understand the universe at its most fundamental level. The hope is that a theory of quantum gravity might allow for phenomena that seem utterly impossible from our current perspective, but which are perfectly consistent within a grander, more complete picture of reality. It's like discovering that the invisible wall in the video game isn't actually a wall, but a doorway that requires a special key. A key we haven't found yet because we haven't fully understood the game's underlying code. However, and this is crucial, even these new physics theories are expected to preserve causality. The causal firewall is not just a feature of our current best theories. It seems to be a foundational principle for a universe that can support complex structures, life, and consciousness. Any truly successful unified theory will likely incorporate it, perhaps not as a direct speed limit, but as an emergent property of deeper, more fundamental interactions. The universe, in its profound elegance, seems to have set up a system that is both incredibly rich and incredibly robust. It allows for astonishing phenomena, black holes, supernovae, the emergence of life, but always within a framework that ensures its own stability. The speed of light is not just a cosmic constant, it's a guardian of the timeline, a silent protector of cause and effect. Our journey through the cosmos, both physical and intellectual, is far from over. We continue to build bigger telescopes, design more powerful particle accelerators, and develop more sophisticated mathematical models, all in the hope of glimpsing the next layer of reality. The human spirit of inquiry is unyielding, and while the causal firewall might seem like an insurmountable barrier, it also represents an incredible intellectual challenge. It pushes us to think beyond our current paradigms, to seek out the deeper truths embedded in the universe's code. So what if the universe does have a secret door? What if the causal firewall isn't an impenetrable barrier, but a gate that opens only to those who truly understand the deepest secrets of space-time? In our next chapter, we're going to speculate a little further, venturing into the realm of truly exotic possibilities that might just skirt the edges of the causal firewall without ever truly breaking it. We'll ask, what if time itself isn't what we think it is? What if there are other ways to travel, not just through space but through the very fabric of existence that don't involve going faster than light at all? It's a mind-bending prospect, and I can't wait to explore it with you. Stay curious and keep dreaming. Welcome back to Dreamy Science, fellow cosmic adventurers. We've been on quite the journey, haven't we? We've wrestled with the unyielding cosmic speed limit, marvelled at the mind-bending reality of time dilation, and stared down the terrifying spectre of time paradoxes. We've even dipped our toes into the tantalizing yet demanding theories of warp drives and wormholes, only to find them guarded by the elusive gatekeepers of exotic matter and the universe's own causal firewall. But here's where the real fun begins, where the scientific imagination truly takes flight. Because while current physics, as we understand it, throws up formidable barriers to faster-than-light travel, it also whispers of deeper truths, of an underlying reality far more intricate than our everyday perceptions suggest. What if the speed of light isn't a final impenetrable wall, but rather a boundary marker for a particular layer of reality? What if there are other paths, other dimensions, other rules waiting to be discovered that could fundamentally change our understanding of space, time, and the very fabric of existence? This isn't about breaking the speed of light. It's about redefining the journey. It's about discovering new physics that might allow us to achieve what looks like FTL travel from our perspective, without actually violating the fundamental principles of relativity or causality. Think of it less as a car smashing through a barrier, and more like finding a secret tunnel that bypasses the barrier entirely. Let's talk about the biggest challenge in modern physics: unifying general relativity and quantum mechanics. On one hand, we have Einstein's magnificent theory of general relativity, which describes gravity as the curvature of space-time, working beautifully on the grand scales of planets, stars, and galaxies. It's elegant, it's predictive, and it's been confirmed countless times. On the other hand, we have quantum mechanics, the theory of the very small, describing the bizarre and probabilistic world of atoms and subatomic particles. It's equally successful, forming the bedrock of all our modern technology, from lasers to transistors. The problem? These two titans of physics, for all their individual triumphs, simply do not play well together. When you try to describe gravity at the quantum level, the math breaks down, spitting out infinities and nonsensical results. It's like trying to describe the intricate dance of individual atoms using the language of planetary orbits. The scales are too different, the rules seemingly incompatible. But what if unifying them, forging a grand theory of quantum gravity, would reveal the true granular nature of space-time itself? Imagine space-time not as a smooth, continuous sheet, but as something woven from incredibly tiny fundamental threads or pixels. If we could understand the quantum foam of space-time, as some physicists describe it, perhaps we could learn to manipulate it in ways that are currently unthinkable. This is where theories like string theory and loop quantum gravity enter the stage. These aren't just wild guesses, they are serious, mathematically rigorous attempts to bridge the gap between relativity and quantum mechanics. String theory, for example, posits that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings of energy. Different vibrational patterns of these strings give rise to different particles. An electron is one vibration, a photon another. Here's the mind-bending part. For string theory to work mathematically, it requires the existence of extra spatial dimensions beyond the three we perceive: length, width, height, and the one of time. We're talking about potentially 10 or 11 dimensions in total. Wait, you might be thinking, if there are extra dimensions, where are they? Why don't we see them? Excellent question, and it brings us to a crucial concept. These extra dimensions might be compactified or curled up to an incredibly small size, far smaller than an atom. They're so tiny that we simply can't perceive them with our current instruments. Think of it like this. Imagine an ant walking on a very long, very thin garden hose. From a distance, you, the giant observer, would only see the ant moving along a one-dimensional line, forward or backward. You wouldn't perceive its ability to walk around the hose. But the ant, existing on the hose's surface, knows there's a second dimension, a circular one, curled up around the main length. It can move left and right in that curled-up dimension, even if you can't see it. Similarly, we might be like the ant, confined to our familiar three spatial dimensions, unaware of other dimensions curled up incredibly tightly, or perhaps even large but hidden from us, like parallel sheets of reality. If these extra dimensions exist and we could somehow access or manipulate them, it opens up truly revolutionary possibilities for interstellar travel. Imagine 2 points in our familiar three-dimensional space and say Earth and a distant star light years apart. In our current understanding, you have to traverse that vast distance limited by the speed of light. But what if there's a shortcut through a higher dimension? Picture a piece of paper with 2 dots on it representing Earth and the star. The shortest distance between them on the paper is a straight line. But if you fold the paper, bringing the 2 dots close together, you could theoretically punch a hole straight through, connecting them instantly. The distance in the higher, folded dimension is effectively 0, even though the distance in the original 2-dimensional space remains vast. This is the essence of how extra dimensions could enable FTL equivalent travel. You wouldn't be moving faster than light within our 3 dimensions. Instead, you'd be taking a detour, a shortcut through another dimension, or by manipulating the very geometry of space-time in a way that's only possible if these higher dimensions are real and accessible. You'd be effectively folding space around you, not pushing through it faster than light. Crucially, this approach might sidestep the time paradoxes that plague traditional FTL travel. If you're not exceeding the local speed of light at any point in your journey, but rather altering the path of your journey through a higher dimension, you might avoid the mathematical implications that lead to time running backward. The causal firewall, the universe's inherent resistance to paradoxes, might still be upheld because you're not breaking the fundamental rule of cause preceding effect. You're simply finding a clever, multi-dimensional way to get from A to B. This isn't a proven fact, of course, it's cutting-edge theoretical physics, the kind of science that pushes the very boundaries of human comprehension. We don't have definitive proof of extra dimensions, nor do we know how to access or manipulate them even if they do exist. The energy requirements for such feats would likely be astronomical, perhaps even requiring the manipulation of quantum fields on a scale we can barely imagine. But the beauty of theoretical physics is that it provides a roadmap, a series of what-if scenarios that guide our experimental efforts and inspire the next generation of scientific breakthroughs. It tells us where to look, what questions to ask. The search for a unified theory of quantum gravity, the hunt for evidence of extra dimensions, these aren't just academic pursuits. They are the keys to potentially unlocking the deepest secrets of the universe, including the possibility of truly interstellar travel. Imagine a future where humanity, driven by its insatiable curiosity, finally unravels these mysteries. Imagine a future where we understand space-time not just as a stage for our cosmic drama, but as a dynamic, manipulable entity. What if we could build vessels that don't just sail upon the currents of space-time, but can reweave its very fabric, guided by the principles of a unified theory? This vision, while still firmly in the realm of science fiction today, is what fuels the minds of countless physicists around the globe. It's the ultimate dream, to connect the scattered islands of life in the universe, to transcend the vast isolating distances, not by brute force against the speed limit, but by a profound, elegant understanding of reality itself. The causal firewall, the universe's self-preserving mechanism against time paradoxes, remains a formidable guardian. But perhaps, just perhaps, these new physics theories offer us a way to respectfully navigate around it, to fulfill our yearning for the stars without shattering the very coherence of reality. What do you think? Does the idea of extra dimensions resonate with you? Does it feel like a plausible path forward, or too far-fetched? I'm always curious to hear your thoughts on these mind-bending concepts. Let me know in the comments below. And if you're enjoying this journey through the cosmos with us, don't forget to hit that like button and subscribe to Dreamy Science for more explorations into the universe's most fascinating mysteries. Next time we'll delve even deeper, exploring the philosophical implications of these grand theories. If we could travel across the galaxy in an instant, what would that mean for our place in the universe, for our understanding of consciousness, and for the very definition of humanity? Stay curious, fellow dreamers, because the universe is always more astounding than we can possibly imagine. Welcome back to Dreamy Science, where we continue our mind-bending journey through the cosmos, probing the very fabric of reality and the seemingly impossible dream of faster-than-light travel. In our last chapter, we ventured into the tantalizing realm of string theory and the profound idea of extra-spatial dimensions, dimensions beyond the three we perceive, curled up, so small they're invisible, or perhaps vast but inaccessible to our current technology. We asked, could these hidden dimensions offer a revolutionary shortcut through space-time, allowing us to traverse unimaginable distances without ever locally violating Einstein's unyielding cosmic speed limit? It's a question that truly ignites the imagination, isn't it? Imagine for a moment that our universe, our entire observable reality, is merely a three-dimensional surface, a brain, as some theories call it, floating within a much larger, higher dimensional space, the bulk. Think of it like a piece of paper. You can draw 2 points far apart on that paper, and travelling between them in 2 dimensions would take a long time. But what if you could fold the paper? Instantly, those 2 distant points are brought together, allowing you to jump from one to the other, with barely any perceived travel in the original 2 dimensions. This isn't just a clever analogy, it's a central concept in some models of higher dimensions, such as the Randall-Sundrum models. If we could somehow access this bulk, step off our 3D brain, traverse the higher dimensions, and then step back onto our brain at a different, incredibly distant point, we would, from our 3D perspective, have achieved what looks like faster-than-light travel. We wouldn't be moving through our space faster than light. We'd be moving around it, taking a path through a larger hidden reality. The effective speed in our perceived 3D universe could be immense, even covering light years in moments. But here's the critical, often overlooked detail that brings us right back to our central dilemma: causality. Even if we could fold space-time like a piece of paper, or navigate through a higher dimensional bulk, the universe's fundamental laws, particularly those governing cause and effect, are incredibly robust. The cosmic sensor hypothesis, the idea that the universe inherently prevents the formation of naked singularities, or, in our context, time paradoxes, remains a powerful guiding principle. So if we take a shortcut through extra dimensions, are we truly safe from creating a grandfather paradox? The answer, as always in theoretical physics, is nuanced and depends on the specifics of the new physics at play. The key lies in understanding that even within these higher dimensions, the local speed of light, the absolute speed limit for information transfer within that specific local region of space-time, must still be respected. You're not moving faster than light in the bulk, you're simply taking a shorter path. The challenge then isn't just finding these dimensions or learning to manipulate them. It's ensuring that any such manipulation, any folding or traversing, doesn't inadvertently create a closed time-like curve, CTC, from the perspective of an observer who remains in our 3D universe. A CTC, remember, is the theoretical pathway that allows for travel into one's own past. If our shortcut, while respecting local light speed, allows us to arrive at a destination before we left, according to some valid frame of reference, then we're right back in paradox territory. This is where the quest for a unified theory of quantum gravity becomes absolutely paramount. String theory, for all its elegance and mathematical beauty, is just one candidate. Other approaches, like loop quantum gravity, offer different perspectives on the fundamental nature of space-time itself, suggesting it might be granular or quantized at its smallest scales. What if at this quantum level the very fabric of space-time is inherently structured in a way that prevents the formation of paradoxes, regardless of how cleverly we try to bend or fold it? Imagine if the universe's causal firewall isn't just a classical speed limit, but a deep quantum mechanical property. Perhaps the rules governing the interaction of space-time at its most fundamental level, the rules that quantum gravity aims to uncover, intrinsically ensure that even if we could access and manipulate extra dimensions, any shortcut would naturally align with a consistent timeline. This means that if you travelled through a folded dimension to a distant star, you would arrive at a point in that star's future, not its past, and certainly not your own past. The universe would, in essence, self-regulate, ensuring that cause always precedes effect. This isn't just about avoiding paradoxes, it's about the very coherence of reality. If the universe allowed causal violations, then the laws of physics as we understand them would break down, predictions would become impossible, and the universe would descend into an incoherent jumble where effects could randomly precede their causes. The fact that our universe doesn't do this, that it seems to operate with such elegant consistency, suggests a deeper underlying principle at work. So the ultimate question for humanity's interstellar ambitions isn't just how to go faster than light, but can we go faster than light in a way that the universe allows? Can we find a loophole that is not a violation, but a deeper understanding of reality's architecture? The existence of extra dimensions, if confirmed, would revolutionize our understanding of space and time. It would redefine our place in the cosmos, revealing a universe far richer and more complex than we can currently perceive. But the tools to truly understand these dimensions, to detect them, to manipulate them, and crucially, to understand their implications for causality, lie within the elusive theory of quantum gravity. This grand unified theory, the holy grail of modern physics, promises to reconcile the vastness of the cosmos described by general relativity with the bizarre probabilistic world of quantum mechanics. It is within this unified framework that we hope to find the definitive answers about the nature of space-time, the true properties of extra dimensions, and whether they offer a path to the stars that respects the universe's fundamental consistency. The search for exotic matter, the theoretical underpinnings of warp drives and stable wormholes would also be profoundly impacted by a theory of quantum gravity. What if exotic matter isn't some rare, yet-to-be-discovered substance, but rather a manifestation of energy interacting with these extra dimensions in ways we don't yet comprehend? Or perhaps the very act of manipulating space-time through quantum gravitational effects could create the conditions necessary for such shortcuts. This is the frontier of human knowledge, the edge of what we can currently imagine. It's a place where science fiction often sparks scientific inquiry, and where the most outlandish ideas sometimes turn out to be profound truths. The universe, in its elegant complexity, seems to be a master of self-preservation, a cosmic architect that has built-in safeguards against its own unravelling. The unyielding speed of light, the causal firewall, the cosmic censor. These aren't just limitations, they are perhaps the very principles that ensure our reality remains coherent, predictable, and capable of fostering life and consciousness. What do you think? Is the universe inherently designed to prevent paradoxes at all costs, even if it means denying us true FTL travel? Or will a deeper understanding of quantum gravity and extra dimensions reveal a path, an elegant solution that allows us to explore the stars without breaking the fundamental laws of causality? I'm always curious to hear your thoughts in the comments below. As we look to the future, the drive to explore, to understand, and to push the boundaries of what's possible remains an intrinsic part of the human spirit. Whether through warp drives, wormholes, or the manipulation of hidden dimensions, the dream of interstellar travel persists. And with every new discovery, with every theoretical leap, we get a little closer to understanding the true nature of space-time and our place within its dynamic, mind-bending tapestry. The universe, it seems, has many more secrets to reveal, and we at Dreamy Science are thrilled to explore them with you. Don't forget to hit that like button and subscribe if you're enjoying this journey into the unknown. Welcome back to Dreamy Science, where we're not just exploring the universe, we're trying to understand its deepest, most enigmatic rules. We've journeyed through the unyielding cosmic speed limit, grappled with the mind-bending implications of time dilation, and faced the terrifying spectre of paradoxes, those causal knots that threaten to unravel the very fabric of reality. We've seen how the universe, through its causal firewall, seems to possess an inherent, almost stubborn resistance to such self-destruction. But what if there's a way? What if the very new physics we yearn for doesn't just enable faster-than-light FTL travel, but also inherently resolves these paradoxes, making FTL not just possible but safe for causality? That's the ultimate hope, isn't it? To unlock the stars without breaking the universe. And it's here, at the bleeding edge of theoretical physics, where we find the most tantalizing, albeit speculative, answers. Let's revisit the idea of extra-spatial dimensions. Imagine, if you will, our universe as a vast two-dimensional sheet of paper. We, as 2D beings, can only move forward, backward, left and right on this surface. To get from point A to point B, we must traverse the distance on the paper. But what if there's a third dimension? What if you could simply fold the paper, bringing point A right next to point B, and then poke a hole through it? You haven't moved faster than light on the paper. You've simply taken a shortcut through a higher dimension. Now, extend that analogy to our own four-dimensional space-time, three spatial dimensions plus time. If there are hidden, curled up, or even vast extra dimensions, dimensions that we cannot perceive or move through in our everyday lives, could they offer a similar cosmic bypass? This isn't just science fiction. It's a core concept in theories like string theory and M theory, which postulate that our universe is merely a 3D brain floating within a higher dimensional bulk. If FTL travel were achieved by traversing these extra dimensions, the physics governing our familiar four dimensions might remain perfectly intact. You wouldn't be locally exceeding the speed of light within our space-time. Instead, you'd be taking a detour outside of it, reappearing at your destination having effectively bypassed the light speed barrier from our 4D perspective. But how would this prevent paradoxes? Think about it. The grandfather paradox, the information paradox, they all rely on the idea of travelling backward along our established timeline. If you step out of our timeline into a higher dimension, you're no longer constrained by its linear progression in the same way. It's like exiting a movie to go to the bathroom and then returning. The movie, our 4D timeline, continues, but your personal experience of time and space was temporarily decoupled from it. Perhaps travel through the bulk fundamentally alters your relationship to our spacetime's causal chain. When you re-enter, you might do so at a point that is causally consistent, or perhaps your very re-entry creates a new branching timeline, a concept we touched upon with the many worlds interpretation. If every FTL journey through extra dimensions automatically shunts you into a parallel universe upon arrival, then you could never paradoxically alter your original past. Your actions would only affect the past of the new parallel universe you now inhabit. This elegant solution allows FTL travel while preserving the integrity of your original timeline, a beautiful workaround to the causal firewall. Then there's the truly mind-bending realm of quantum gravity. General relativity describes gravity and the large-scale structure of space-time, while quantum mechanics describes the microscopic world of particles and forces. They are currently incompatible. A unified theory of quantum gravity, like string theory or loop quantum gravity, aims to reconcile them, revealing the fundamental nature of spacetime itself. What if spacetime isn't the smooth, continuous fabric Einstein envisioned? What if at the Planck scale, an unimaginably tiny scale far smaller than an atom, spacetime is actually granular, foamy or pixelated? Imagine it less like a perfectly smooth sheet and more like a bubbling, effervescent quantum foam. If you were to try and travel through this quantum foam at speeds exceeding Kawuk, perhaps the very act of doing so wouldn't break a continuous barrier, but rather involve a series of quantum jumps or tunnels between these spacetime pixels. In this scenario, the traditional rules of classical causality, which rely on continuous trajectories through smooth spacetime, might simply not apply in the same way. Consider quantum entanglement. It's a phenomenon where two particles become linked, sharing the same fate no matter how far apart they are. Measure the spin of one, and you instantly know the spin of the other, even if they're light years apart. This instantaneous correlation appears to be FTL communication, but critically it cannot be used to transmit information faster than light. You can't send a message. But what if the very fabric of spacetime at its most fundamental quantum level is entangled? If FTL travel involved somehow exploiting this inherent entanglement of spacetime itself, it might bypass the classical speed limit without violating causality. Instead of physically traversing the distance, you might be teleporting your quantum state or even your entire being by leveraging these pre-existing instantaneous connections within the quantum foam. How would this prevent paradoxes? Here, the probabilistic nature of quantum mechanics could be our ally. In the quantum realm, things don't have definite states until they are observed. Particles exist in a superposition of possibilities. What if a paradoxical FTL journey simply cannot collapse into a definite, consistent reality? Imagine you attempt the grandfather paradox using quantum gravity-enabled FTL. You arrive in the past, aim to prevent your grandparents from meeting, but the universe, at this fundamental quantum level, might simply reuse to allow that particular measurement or collapse to occur. The quantum state representing your existence might become entangled with the quantum state representing your grandparents never meeting, creating a superposition that cannot resolve into a stable, self-contradictory outcome. Perhaps the universe's causal firewall isn't a hard classical barrier, but rather a quantum mechanism. It's not that paradoxes are prevented by some external force. It's that the laws of quantum physics themselves make paradoxical outcomes fundamentally unstable or impossible to realize. The wave function of the universe simply cannot collapse into a state where causality is violated. It would be an inherently forbidden state, much like an electron can't exist in a forbidden energy level. This is where Stephen Hawking's chronology protection conjecture could find its ultimate foundation. It's not just a conjecture, it's an emergent property of the unified theory of everything. The universe, at its most fundamental quantum level, simply enforces self-consistency. Any attempt to create a paradox would be met with an insurmountable quantum barrier, perhaps through a burst of energy, a collapse into a black hole, or a probabilistic outcome that always resolves into a paradox-free reality. The beauty of these new physics approaches is that they don't necessarily break Einstein's rules. They transcend them. They offer mechanisms where FTL equivalent travel is achieved not by directly violating Q within our familiar spacetime, but by either taking a shortcut through dimensions beyond our perception, or by leveraging the deeper, quantum-level structure of spacetime itself, where the very definitions of speed and time might operate under different, more fundamental principles. Ultimately, the quest for FTL travel is inextricably linked to our understanding of time, causality, and the very nature of reality. It's a journey into the unknown, a grand scientific adventure that forces us to question everything we thought we knew. Will we find these extra dimensions? Will we unlock the secrets of quantum gravity? And if we do, will the universe finally yield its secrets, allowing us to reach the stars without unraveling the past? The answers, my friends, lie in the continued pursuit of knowledge, in the relentless curiosity that drives us to ask what if, and to push the boundaries of human understanding. This is not just theoretical physics, it's the very future of humanity's place in the cosmos. If you're as fascinated by these mind-bending possibilities as I am, and if you believe that science holds the key to unlocking these cosmic mysteries, then if you'd hit that like button. Subscribe to Dreamy Science so you don't miss our next deep dive into the universe's most profound questions, and please share your thoughts in the comments below. What do you think is the most plausible way to achieve FTL without paradoxes? Or do you believe the universe's causal firewall is truly impenetrable? I'm always curious to hear your perspectives as we navigate these incredible frontiers together. Till next time, keep dreaming and keep exploring.